Now this problem is in continuation of the problem B3, and the part A I have solved under the heading problem 6 part A, and here we are going to solve this part B. And the part A was about the cleaning of the solar system due to the solar radiation, where solar radiation is exerting pressure, radiation pressure on the particles. Now the Poynting-Robertson effect acts as another mechanism for cleaning out the solar system. In the first part of the question, he is asking that assume that a particle is in circular orbit around the sun. Find the speed of the particle v in terms of solar mass. Distance from the sun is r, and any other fundamental constants we can use. Clear? Now we know that this is sun, and here we have the particle, and the distance between the sun and the particle is given r. Now this particle is moving around the sun in this circular orbit with certain speed v. Then we have to find out this speed v. So at any instant of time, the gravitational force that is acting on the particle is given by this Fg. Clear? So this is gm, mass of the sun, mass of the particle, divided by r square, and this force is responsible for particle to move in the circle, means this force is acting as a centripetal force. So we can write this as mv square by r, and solving this we will get v, the desired result for the speed of the particle, and that is equal to g into solar mass divided by the separation and its under root. Clear? So this is the speed with which the particle is orbiting around the sun. Now in the second part, he is saying that because the particle is moving, the radiation force is not directed at the sun. Find the torque tau on the particle because of the radiation pressure. You may assume that v is very much less than c. Now in order to understand this situation, let's picturize it, that this is the sun and this is the circular orbit, and at any instant of time, suppose the particle is here. Now this is the radius at that instant, and the solar radiation is in this direction. Clear? Now the direction of motion means this is the direction of velocity of the particle. I am denoting it with Vp. This is the direction of motion of the particle at that instant, and radiation is along this line, and also the radiation is traveling in this direction with c, means the speed of light. Clear? Now what he is saying, that the radiation force is not directed directly away from the sun, means the radiation pressure or radiation force is not directed along this line. Now along which direction this radiation force is, for this we have to consider the direction of relative velocity, direction of relative velocity of radiation, direction of relative velocity of radiation with respect to the particle. Clear? We have to look out for the relative velocity, direction of relative velocity of radiation with respect to particle, and we can write mathematically this situation as VRP, and that is equal to VR minus of Vp, and instead of writing minus Vp I am writing VR minus Vp. Now where is this minus Vp? So the minus Vp will be in this direction, so this is minus Vp. Clear? And the resultant of this VR, that is the velocity of the radiation, which is c. So the resultant of this c and this minus Vp is along the resultant of these two vectors. So this is the direction of VRP, as this is the direction of VRP. Now if we take this angle as theta, so from here we can write tangent of theta, and that is equal to perpendicular by base, so it is Vp divided by VR. Now Vp, let this Vp, the velocity of the particle, its magnitude is say V, and the speed of the radiation, that is c. And also it is given that this V is very much less than c. This means this theta is very small, so from here we can write that theta is equal to V by c. Clear? So this result will help us to calculate the torque tau that is acting on the particle due to radiation pressure. Now the direction of the radiation pressure, is along this direction, the direction of relative speed of the radiation with respect to the particle. So if this is the direction of the radiation pressure, means this is the direction of force exerted on the particle due to the radiation, then this component is cos component, and the component along the tangent to this path of the particle is the sine component, and I am assuming the force acting is F, and the component along this direction is F sine theta. Clear? And this distance given is r. So in order to calculate the torque that is acting on the particle, so from here we can write tau, the torque, is equal to force into perpendicular distance, and this force here is basically F sine theta, so we will write this as F sine theta. Clear? So this force is acting in this direction and it is perpendicular to this separation, so the torque acting on the particle is this. Now again theta is very small, so we can write this equation as F r theta. So by substituting the values of F and theta, we will get the desired result. Now this F we have calculated earlier in part A, and that we have calculated that this force due to the radiation pressure was V by C. This was the power, radiation power, divided by 4 pi r square C into Q pi r square, that we have calculated in part A of the question in the earlier video, problem 6. And this is force, this is the separation r, and theta we have this V by C. And solving this we will get V by C into solar value, this is L, 4RC into QR square. Clear? Now if you watch this diagram carefully, you can also observe that the direction of the angular velocity here in this situation, the direction of angular velocity is towards u, and if you observe the direction of torque corresponding to this force, now the direction of this torque corresponding to this force is away from you. This means this is basically anti-torque, which is trying to decrease the speed of the particle, so we will put a negative sign here. So this is answer to our second part, in which we have to calculate the torque that is acting on the particle due to radiation pressure. Now in this third part, he is asking that since tau is rate of change of angular momentum with respect to time, the angular momentum L of the particle changes with time. As such, develop a differential equation to find dr by dt, the rate of change of radial location of the particle, and you may assume the orbit is also quasi-circular. So we have to find this dr by dt, means the rate of change of radial location, because the solar radiation are trying to sweep those particles away or trying to blow them away. This means if the radiation pressure is sufficiently larger than the gravitational force, the this distance r will keep on increasing. Clear? So we have to find out here this dr by dt. So from the definition of angular momentum, we have this angular momentum L, that is mvr. Clear? So if we substitute the values for m is the mass of the particle, that is density of the particle into volume of the particle. V we have calculated in part 1, that is under the root g into solar mass divided by the separation and into this distance r. So we have this result, and solving this we will get 4 by 3 pi rho r cube under the root gm by r. Clear? Now in order to calculate the desired result of dr by dt, we have to differentiate this equation on both sides, and differentiating this equation on both sides we will get dl by dt, and that is equal to d by dt into this quantity. Clear? So we will put this quantity here, and if we solve it, this dl by dt is tau, and tau we have calculated here. So we have v by c L solar 4rc qr square, and differentiating this equation we will get 4 by 3 pi rho r cube under the root gm by r into 1 by 2 dr by dt. Here we have differentiated this under root r, so from here we have got this part, and if we solve this equation we will get finally minus 1 by c square L solar divided by r into q, and that is equal to 8 by 3 pi rho r dr by dt. So this is our desired differential equation of part 3. Now in part 4 he is asking that develop an expression for the time required to remove particles of size r that are around 1 centimeter and density 1000 kilogram per meter cube, originally in circular orbit at distance r, and that separation is equal to the distance from the sun to the earth, and use the numbers below to simplify your expression. Now here if you observe that this r is almost 1 centimeter, this means the size of the particle is very much greater than the wavelength of the radiation, and under this condition we are given with q equal to 1 in part A of the problem. Now in order to get the expression for the time we have to integrate this equation. So in order to integrate we will take this dt on this left hand side and this r on the right hand side, and if we solve this integrating dt we will get t into 1 by c square L, and q we have taken this q as 1, and it is equal to 8 by 3 pi rho r, and integrating this r which is taken on this right hand side we will get r square by 2. Clear? And finally the expression for the time t is 4 by 3 pi c square divided by L into rho r into capital R square, and substituting the values of these quantities, finally we will get this t approximately 7 into 10 raised to power 6 years. So this much time is required to blow away a particle of this much size. Clear?